So hi guys, how are you? Today we are going to cover all those deep learning concepts from that basic one concept to the advanced level, and we are going to cover all those small concept, and at the last we are also going to cover whole project, how to discuss that project to the interviewer and all those related concept. So please be focused. So it will be a short duration video, and in that we are going to cover all those questions mostly interviewer will ask, and how you have need to give like that one. So I will add a name to the file that deep learning, and because mostly in the interview they asking all those questions related to that one. Okay, so we will start with the deep learning. So initially they will ask what is deep learning and how its effects are different from that machine learning and that type. Okay, so you need to know very well that what is deep learning. So it's basically main part is artificial intelligence or AI. So this is AI you can consider as. Then in that AI it's another part, or it's a subset of AI. It's machine learning. Okay, and within the machine learning there is come a deep learning. Okay, so deep learning is a part of machine learning and its comes belong to that one. And deep learning will consist of that artificial neural network, then convolutional neural network, also it will consist of natural language processing, also it consists of RNN. Okay, so they may be asking to ask what is the difference between artificial intelligence, then machine learning and deep learning. Okay, so main the difference is artificial intelligence is the main and others are the sub branches of its. And in the machine learning there are two types: supervised machine learning and another one is unsupervised machine learning. Okay, and deep learning is a part of machine learning, and in the deep learning there are also two parts, that's artificial neural network and convolutional neural network. Also along with that there is a natural language processing parts. In that supervised machine learning there are various algorithms such as linear regression, then logistic one, then random forest or a decision tree, then k nearest neighbor. Okay, then also you can consider a support vector machine. Then there are various such as XGBoost, means those are all boosting, gradient boosting algorithm, ADA boost. Then okay, then gradient boost. Please be prepared very well for all those, because interview will going to ask definitely question on them. And in the unsupervised there are various types such as clustering algorithm. Here you do not require to be output or target variable, automatically machine will going to make a classification based on the centroid. So here is k clustering, then hierarchical clustering, then db scan also here. Okay, then principal component analysis, it's also very important for the dimensionality reduction purpose. Okay, and also other also there, but those are very important and interview definitely going to ask on that. Then please be prepared for the cost function of everyone. For here also two subtypes form, that regression type and classification type. Where in the classification target variable is in the categorical format. So for that classification confusion matrix you should do very well, and it's every interview will going to ask about that precision recall, where is true positive, when false positive is important, when false negative important, like that. And in the regression they will definitely going to ask about r square, adjusted r square, then root mean square error, and why those are important, those concepts. Okay, so this one is a basic or short revision of machine learning. Okay, So I have already covered all those videos related to the machine learning, but now we are going to see main focus for the deep learning, and we will do. So deep learning is a part of machine learning. Here actually in the deep learning we have do not require to do a whole process like machine learning, so it's a very deep and it's based on that neural network, how that human brain or like works. Similarly it works. So it consists of neurons. Neuron is one unit where actually it consists of two parts. First one is the summation of all those weight and biases are provided here in that part, or indirectly we give here input, and here is in the hub part there is activation function, and through that activation function it will going to give output in the form of 0 1. Indirectly we can call it as a classification type, or it can give output in the regression type also. So for that purpose various functions are there. For that regression there are functions that linear unit activation function can be used for the regression purpose, and for that classification purpose various functions there are, and most of the use that is sigmoid if the classification is only binary type 0 and 1, and if the classification type is a multi classification then we can use a function called as softmax. Okay, so it's used for the multi classification. So we are going to see all those, but I have just initially told that what is neuron, and all those neurons are connected internally with each other. So deep learning mostly consists of in this way I will show you. It consists of, first one is the input layer. Okay, so in that input layer there are many number of neurons, and the number of neurons is determined by, I will write here, number of neurons is equal to the number of features in your that project. Okay, so you know very well what are the features, or indirectly it's column. So here in that input layer there are that number of neurons, that is it's equal to number of features. Okay, so here for that neuron we feed the so many number of features. Suppose if your column contains or project file contains 24 number of features, then there should be 24 neurons initially. Okay, so after that in that input layer, so that layer is called as I will tell you, that layer is called as input layer. Okay, please remember input layer, and be remember here input layer it does not contain activation function. Okay, here we don't require to give a activation function to the neuron or that input layer, because here we do not provide weight and biases. We do not add in the input layer weight and biases. So here actually weight and biases are added. So weight and biases are added in the hidden layer. Okay, so that layer is consist of hidden layer. That layer is invisible or we cannot see, and in that hidden layer there may be many layer of neutrons, such as there may be 1 layer, 2 layer, 3 layer, 4 layer, and actually there is no way how many layers should be in that hidden layer. But if you increase the number of hidden layers, then your project may give a better accuracy, but there are very high chances that it can become a too complex and its time complexity issue will increases. So we should always keep that number of hidden layers should nearly equals to the 3, 2, or according to condition maximum 4 or 5. Do not go beyond that one, because as per the research they are using maximum 3 hidden layers. Okay, and in the hidden layers the number of neutrons, how many number of neutrons should be in that each layer, it's depend upon, there is also no rule, but mostly those number of neurons are taken indirectly in the range of between input neurons and output layer neurons. So suppose if your input number of neurons in that input layer is 24, and suppose if your output is only classification type, so there will be only one neuron. So we can divide that 24 by 2, so it's become 12, 6 and 6. So we can take all those number of neurons in that way. So that the first hidden layer should contain that 6 neurons, then middle layer should contain that 12 neurons, and the last layer should contain the 6 neurons. Okay, so indirectly here neurons are connected in that this way, and this way, and we are going to do this one. So after that we are going to do here neurons are connected in this way, means every neuron is internally connected with each other with every alternate neuron. So there is a very complex structure. Okay, so you are going to see how those neurons are connected. It's like that one, it's become a messy type structure. And remember, the hidden layer neurons contains the activation functions, and there are so many activation functions such as Rayleigh, leaky Rayleigh, then sigmoid, then 10H. Okay, you know that very well, and we are going to do a revision of them also. Okay, and after that there is a last layer, or we can call that layer as output layer. Okay, and that output layer is the number of neurons in that output layers depend upon how is your output. Suppose if your output is in the binary format, suppose if there is a project about that credit card for fraud detection, and the output column or target column just contains that is fraud happened or not. So output is only binary format, yes or no. So it's in the condition like 0 and no. So definitely we are going to use here sigmoid function, and for that purpose we have just required only one neuron. Remember, only one neuron. Suppose if there are a multi-classification problem and your output is like high, medium or low type, then it's become a multi-classification type problem. So here we requires two neurons. Okay, so two neurons depending upon your that classification type, how its classification is going on. And suppose if you are going to use that function, it's called as softmax, then it's used for the multi classification, then once again here number of neurons going to become 1. I hope you have understand that's very well how that's happening, and how we are going to select that activation function and like that one. Now we are going to see now detailed process about that neuron, how that internal neuron works. So already I have told you about that it's the internal structure of neuron, and it is divided into half part. So first of parts here actually we are going to provide the input, and in that input actually we are going to provide the weight plus bias. Okay, so W is for weight. So actually how we provide the weight to the deep learning neural networks, so there are various types. If you are going to use the activation functions such as Rayleigh, then leaky Rayleigh, okay, then Elu, then P Rayleigh. Okay, for that purpose we are going to do a weight addition functions. We are going to use the weight addition functions, and those functions name are HE normal, or you can call it as a He normal, and another one is HE uniform. Okay, please be remember, while doing actually programming you have need to add all those functions name in that project, means you have need to add those activation functions in your code file, then it will going to do add those. Okay, so for that type of activation functions you are going to use that one, and means you are going to update weights through that one. And suppose if your weights are like that one, Suppose you are going to use the activation functions like sigmoid or softmax or 10h. Okay, so those are the what we can call classification type functions. Okay, classification type activation function. So here you are going to update weights by using a function. It's called glorate normal, and another one in name is glorate uniform. Okay, so through that function actually we are going to give the weight and biases to that function. Okay, so for the sigmoid function the formula is z is equal to 1 plus e raised to minus y. Here y is that value, y is equal to mx plus c, and in the deep neural network for slope indirectly we are going to call that weight, and for c we are going to call as bias. Remember here bias value can be 0. Okay, bias value can be 0 but weight value cannot be 0. So we are going to add some bias indirectly if that weight value becomes 0 in the neural networks. Then to avoid the whole problem of that unit we are going to add some biases in that. Okay, so that's the main basic function activation functions, that how that summation and addition is done in that. So here actually we add that wi bi. So wi is the weight, bi is the bias, and how we are going to add bias for that all functions by h normal, h uniform, and for that sigmoid or classification function by using glorate normal or glorate uniform. Okay, so you learn about that how here bias addition is done, and after that there is a function in that second parts and it's called as activation function. And activation functions consist of that all those activation functions: Rayleigh, Rayleigh, ilu, p Rayleigh, sigmoid, softmax. Okay, so now we are going to start all those, we are going to learn all those activation functions and what is the role of all those activation functions. Okay, so I will write here activation function. Be remember it's a very important part of activation function, and every interview will going to definitely ask all those questions on that activation functions. Okay, so what are the activation function and what is the use of them? Okay, and use of them. So activation functions are the functions which actually going to calculate all those value, and those value they are going to convert into the either 0 or 1 or 0 or more than 1 or into the range of -1 to 1. So for that 0 to 1 range there are activation function is called as sigmoid. Okay, if the range is -1 to 1 then it's called as 10h. If the range is between z of max 0 comma z then it's Rayleigh. If the range between the value of max 0.001 comma z, here we give some value, then it's become a Rayleigh. If the values become max 0.p comma z, where 0.p is the parameter or some constant value we adding to avoid the problem of deep neurons, then it's become a parametric Rayleigh. And when the value becomes max of log of 0 point that p value comma z, so it's become a ilu. So ilu is a exponential linear unit. Okay, so we are going to also do some curves for them. We are going to learn what is the sigmoid function. Okay, we are going to take initially that sigmoid activation function, and I will going to show you how that sigmoid activation function works. So that activation function is mostly used for that purpose of classification. Okay, So it's used for that classification. If your output value are in the binary format, or those are in the format of 0 or 1 or yes or no, in that format, then we mostly use that sigmoid function, and it's frequently used most of the time if your problem is binary classification, because it's faster, it's required less computational time, and it's very accurate. Okay, now let's see what is the graph of that function. So it's y-axis, and that one is the x, this one is the y. So you know very well, in the machine learning model also we have learned about how is the graph of that sigmoid function. So those are the value of 0 to 1. So graph of that sigmoid function is like that one. Okay, so it's graph like this one. So this is a S type graph where this middle point is 0.5. Okay, so sigmoid function only going to give you the value between 0 to 1. Suppose if your value goes beyond that -1, then it will not going to give you a value. And also I will correct that modify graph. So its values are like this one, 0 to 1. So it's give vertically values, not along the x side. So its curve become be the like this one, S type curve. Yes, just wait a minute. This is x axis. Okay, so this gives the value between 0 to 1 only. Now we are going to see what are the disadvantages of that one, why we are not going to use only sigmoid and we are going to move towards the another one. So there are various issues. I will write here disadvantages. Look, you should know the concept of that learning rate, and we actually update the weights. New weight is equal to old weight minus, that's the learning rate, with respective loss to the learning rate of previous learning rate. Okay, so in the sigmoid function what happens, when actually we are going to do a forward propagation, that through the epoch is equal to one epoch is equal to one forward propagation plus backward propagation. Okay, so what happens in the forward propagation, we actually going to check the bias, or we are going to calculate the error. How is our predicted value is different from y actual value, and we are going to consider it as a loss, and to minimize loss. Okay, so in that forward propagation we are going to just calculate the loss, and in that backward propagation we are going to update all those weight and biases such that once again when forward propagation will happen, that time that loss will going to become a very less. So for that it's called as weight updation, and that happens on in backward propagation. Okay, it's not going to happen in the forward propagation. So weight updation and bias updation is happen in the backward propagation. So here I have given all those. Okay, so be please careful, interview is going to ask you all those questions. So in that sigmoid function what happens, it will going to calculate your error rate or anything, or loss rate or bias in the forward propagation. But when it will going to do a backward propagation, the derivative of that is the very important, the derivative of sigmoid function will be always in the range of, please remember, that's very important point, only 0 to 0.25. so you will going to get that the only fluctuation value of that sigmoid function in the range of 0 to 0.25 if we are going to take its derivative. And in that updation, weight updation and byte updation, actually we are going to calculate the loss with respect to the all those weights by taking derivative, and the value of sigmoid function going to vary between only 0 to 0.25. and when we are going to multiply that 0.025 to the learning rate, then that value becomes a very less, that's in the form of 0.001 or like that one. So here what happens, new weight is equal to becomes a old weight indirectly. So here is no change happens indirectly, or that change is very small, infinitely small change. So that problem is called as a vanishing gradient problem. And every interview is going to ask you that problem, vanishing gradient problem. Please be remember and be prepared for that one. Sigmoid function drawback is the vanishing gradient problem, because it will not going to update weight and biases in the forward propagation, because the derivative of sigmoid function is lies between only 0 to 0.25, and the changes made by all those, it's very infinitely small, and there is no change between the new weight and old weights. So it indirectly vanishing gradient problem, and that's problem is called as vanishing gradients, because there is no change in the weight updation, so there will be no change in the loss. And actually here our main target is to reduce the loss. Okay, I hope you have got that concept very well, and I have explained that concept in the layman term. Okay, so to avoid the issue of that vanishing gradient problem, we move towards the function that's called as tan h function. Okay, so it's a tan h function. So to overcome the issue of sigmoid function, where sigmoid functions values were between the 0 to 1, now the tan h functions value will lies between the -1 to 1. So the graph of tan h functions will be like that. Here is a 0, here is the 1 range, and here is the -1 range. So graph of tan h functions will be like that one. And please remember, we are going to see why we are going to use the mostly tan h functions as compared to sigmoid functions, and its advantages for that sigmoid one. So tan h, it's a geocentric function, it's a geocentric. Okay, geocentric means it passes through the geocentric, so the all the addition or that updation through the mean will be equal to 0. That's not happens in the sigmoid functions. So it's the geocentric function. First one, advantages. Actually the range of tan h functions lies between -1 to, okay, range is -1 to 1. So sigmoid function was giving the value between only 0 to 1, so here it can give a value between -1 to 1. So that's one, the another one advantage. And also it will going to minimize the problem of vanishing gradient descent, because here the derivative of tan h function is range is much more than the sigmoid function. Also here is also going to happen that vanishing gradient problem, but as compared to the sigmoid one, it's far better, and it will going to do some updation and changes in the weight as compared to the sigmoid function. Also vanishing gradient issue, okay, but we'll going to make changes, better than sigmoid, okay. So for that purpose we use that tan h. So most of the time you definitely say to the interviewer that more than sigmoid we have used that tan h function, because it's a geocentric function and it's also going to solve the vanishing gradient problem, and also its value range is far greater than the sigmoid. so definitely you will going to make an impression on that interviewer very well and accurately. Okay, now we are going to see towards so tan h and that sigmoid. Okay, all those are the classification type functions. You should use those functions in the output layer only if your output is in the categorical type. Output is in the categorical type. Okay, and not for the linear type, because those are the what's we can call classification type functions. Okay, and we are going to learn that another one function for that categorical one. So I will make a here box. Okay, those are the categorical type function, and also I will going to add here one extra categorical function, and that is a softmax. Please be remember, because I am at once taking all those categorical type functions and with variable explanation. So softmax function is used for that multi-classification purpose. So you cannot use that sigmoid or tan function for the multi-classification. Those are basically mostly used for that binary classification. So softmax is used for that multi-classification problem if your output is categorical variables are greater than binary. So main advantages of softmax for its use for the multi-classification, it's a zero centric. But here is one issue that softmax not one issue, but it can be used with suppose if there are so many number of features, then you can use, and that formula for that softmax function is like that: e raised to z upon e raised to az plus e raised to bz plus e raised to cz, that like, and in this way I think it's make the classification type. Okay, so that's it about that one. And its value lies between all those multi-classification type. Okay, so I think we have done all those classification type activation functions. Now we are going to see mostly and very important functions such as other activation functions, and mostly those are used, and I will going to give a name that Rayleigh, first one, then leaky Rayleigh. Here is a very small difference between Rayleigh and leaky Rayleigh. In the leaky Rayleigh, we just add some negative values to avoid the dead neuron issue. Okay, then another one is that P Rayleigh, or it's called parametric Rayleigh. In the leaky Rayleigh, what we do here, we just add a small negative value. So here function's value will be 0.001 comma that z. In the P Rayleigh, instead of that 0.001, we give that parametric value. So that value can be 0.00001 or like that one. Okay, and here z is the any positive number between 0 to any number. Okay, but when we take the derivative of that one, then its value lies between the range of 0 to 1. Okay, but before that derivative, all those values lies between 0 to any positive number. Then another one is advanced one is the ilu. So be prepared to remember that long form. It's exponential linear unit. Okay, and after that there is other functions such as mostly those is, but okay, we will going to learn after that is Swiss and other one. Okay, so we are going to learn about that Rayleigh, and once you learn Rayleigh, you will going to get all those functions, other functions automatically. Okay, so I will plot that graph for that Rayleigh. So it's a y-axis, it's a x-axis, and the graph for that Rayleigh is whenever the value become less than 0 or 0, automatically Rayleigh going to make all those values as a 0. But if any numbers greater than 0 or positive numbers, then Rayleigh will going to give you a straight line that one. Okay, for any number. So it's a 1 number, it's 2 number, it's 3 number, it's 4 number, it's 5 number. So the range of Rayleigh functions lies between 0 to, it will start, its minimum value will be 0 and not less than the 0, and maximum value will be z, and z is the any positive number. Okay, so it can be written like that one. Function name is equal to y is equal to, okay, and when you take the derivative while the updating weight and biases, you need to take the derivative. So I will write here dw, so dl divided by dw, then its derivative range varies between only 0 to 1 and not 0 to maximum. Okay, so we are going to say advantages of Rayleigh over that sigmoid and other functions. Okay, so in the sigmoid functions what happens, it will going to give value only between 0 to 1. So in the Rayleigh it will act as a linear type also function, means linear regression type functions or regression type functions. So its value varies between 0 to any positive number, max of any positive number. Okay, another one function is, here is no issue of vanishing gradient occur, no issue of vanishing gradient. Why here is no issue of vanishing gradient? Because in the sigmoid functions its derivative value lies only between 0 to 0.25, and that's why there is a very small or simultaneously change in that sigmoid functions weight updations. But here the derivative value lies between 0 to 1, so here that calculated derivative value will going to give us some uh, large number, and that's why there will be a weight updation done, and hence it will not going to do a vanishing gradient problem. Okay, and it's faster also. Okay, it's faster also, but we are going to see some its negatives. What are the its negatives? So be prepared to ready. It will going to create a dead neuron. That is the very important interview going to ask you, and you should know very well. Dead neuron will going to happen in the Rayleigh if in your problem there are some negative values. So whenever through that neuron, it's a neuron, and suppose here is all those weight updation, and we give the bias and weights, and here is that Rayleigh function or Rayleigh activation function. Suppose in the forward propagation we calculate the loss by predicting how actual values, predicted value is different from the actual value, so we got the loss, and in that backward propagation we try to update those loss. But whenever in that backward propagation we got the negative value of any weight or bias, then Rayleigh will suddenly going to become a to create that neuron as a dead neuron, or it will going to stop that neuron for permanently in that neural network, and it will not going to activate, because once it going to touch that zero value or anything less than 0, then that neuron will going to stop working, because Rayleigh functions will going to give a value between only above 0 or 1, and that's the main issue of dead neuron. So if your problem is consist of the value of positive negative, then you should not definitely going to use that Rayleigh one, and to solve that problem we are going to see that liquid Rayleigh. So dead neuron problem. Also here is a problem of exploding gradient. So we are going to see actually what is exploding gradient. So let's see, we are going to update the w weight new to minimize that losses, and here is a w old rate, here is that learning rate, and here is we update the loss based on that w I or w old. Look, see, it's all depend upon the value of learning rate, and here is the value of dw. Now the range of derivatives that Rayleigh functions lies between 0 to 1, but sometimes what happens here, because of if suppose you have got the loss some extra large in that prediction in the sum layer or in that output layer, then your that learning rate will going to not going to change, but there will be sudden increase in that weight. Here is a sudden increase in that weight, and that sudden increase or sudden decrease in that weight will going to create more changes in that all that step. So, and because of that, here new weight will be with changes with very huge number, and that's called as a exploding gradient issue. So here you will not going to get the smooth curve, or it will not going to find the proper weights. So here will be some jumps in that your value, and it will not going to give proper value. So that exploding gradient problem issue will going to happens because a sudden changes, a very large change in that updated values of that weights. Okay, so to solve all those issue, here some, always try to remember that in that deep learning or that artificial network, always there is another way to solve that one, and you should remove all those processes in this way. So here what happens, the next concept comes a leaky Rayleigh. So leaky Rayleigh mostly used to solve the dead neuron issue. So initially we have seen here how that it's a Rayleigh function graph. Okay, Rayleigh function graph. So we have seen here Rayleigh function graph is like that. It will going to stop from that 0, and here it will going to create a dead neuron. Okay, and here it will going to give a value. But for that leaky Rayleigh, what we are going to create, we are going to give a very infinite small value. Okay, negative value, it may be 0.001, and after that it will going to predict all those positively. So because of that zeros, we have provided here some negative value to that function, then it will not going to create. So it will not going to create dead neuron, not create, but it will not going to make neuron as a dead, not going to create dead neuron. Okay, so here will be no issue of dead neuron. That's the very strong point. Okay, here is still also the issue will going to about the exploding gradient, and to solve that one we will going to do a ELO or exponential linear unit, and after that leaky Rayleigh, there is another one is the P Rayleigh. P Rayleigh is equal to P Rayleigh same as leaky Rayleigh, except in the leaky Rayleigh we give the value between 0.00 minus 1 like that one, but in the P Rayleigh there is a predefined value, means according to you give any value. That's the difference, nothing else. Okay, and so in the last function is the, and that one is my favorite one function, very favorite one, and we call that function as just take, I will change color combination, that it's ELO. The long form of that ELO is exponential linear unit. Okay, so we will going to see its graph. Okay, we have already seen that graph of Rayleigh, leaky Rayleigh, P Rayleigh. So its graph will be like this one. So you will going to see that how that graph is a curve shape. So please be remember to mention curve shaped graph. Curve shaped graph will be here. And why that curve shaped graph is happened, because of log to the e, and we are going to provide all those value in the exponential linear unit. So because of that whole curve is getting converted into the graph format. So here will be no issue of so that is the positive point, no issue of exploding gradient, because of that smoothness of curves, all those weight and biases values will not going to explode, such as those values happens in that sigmoid function or Rayleigh or Rayleigh. such that because here is a sudden steep hike, and in that exponential linear unit it's a curve shape graph, so there will be no sudden hike or spike in that, and it will going to solve exploding gradient issue. Also because of it's also going to accept the negative value, so here will be no issue of dead neuron, okay. So that's the positive of all those. So I hope you have understand what is ELO or its why it's fair. So remaining one is the Swiss is also similar to the that Rayleigh, but be remember for that it's required more than 40 number of features, it requires more data, okay. And last one is the softmax, and we have already learned that one. So all those are the activation functions, okay. And there is another one is activation functions. If your output is the regression type, then it's called as a linear activation function. If your output is in the continuous value, then you should use in the output neuron that linear activation function. And if your output is a categorical value, and for that categorical, if value is lies between 0 to 1 or binary, then simply use tan H or sigmoid. And if it's a multi-classification, then use softmax. And which one is the best then? Which one is best activation function? Though ELU is the best activation function, still in the real life ReLU function is preferred mostly because it's more efficient, faster. Here is a no issue of logarithm, so it's make a calculation faster, and it's required less computational time. And if your problem is not going to give the value between any minus side, then ReLU is preferred. And if there is a value lies between varies between -1 to 1 or like that, then you should refer ELO. So I hope I have covered all those activation function. I have covered neuron, and also one is term here is perceptron. So perceptron is nothing but a one single unit of neuron, and I have already told the working of neuron. So please remember, interview will going to ask you how neuron will going to work and what are its stages. So please be remember, neuron is divided in two parts. So in initial parts we provide the weight and biases, and in the second parts it's going to apply that activation functions. Suppose if your weight and biases value is greater than 0.5, then it will going to give a one value if you are going to apply the sigmoid function, and if your value is less than 0.5, then it will going to give you a 0 function, okay. So likewise it will going to give all those output, and all those neurons are interconnected with those each other. So another one is I am going to once again explain all those layer type. So it is the input layer, okay. So those are the hidden layers, and those are the output layers, okay. So all those layers are connected in this way, okay. So I will going to tell you some important points. Please remember, input layer will not going to contain activation function, because here we are not provide weight and bias. So weight and biases are actually provided in between hidden layer and input layer. Weight and biases here also provided weight and biases, okay. And also remember, in the output layer there will be a number of neurons determined by number of neurons in output layer is equal to number of output unit, okay. If it's a binary, then there will be only single neuron. If it's multi classification, then based on that classification there should be number of neurons. And if it's a regression and its output, then also there will be based on that number of outputs, okay. So that's the most basic difference. And please remember, epoch is equal to forward plus backward, okay. And in that sigmoid function there will be no backward propagation will going to happen, though backward propagation will happen, but there will be no any change in weight and biases. So it's a vanishing gradient problems. And please remember, in the backward propagation, so only weight and biases are update, and forward propagation we're going to do to check bias or loss. Okay, so forward propagation will happen only from input side to the output side, and backward propagation always happens in the reverse direction, from that backward sides toward the input one sides. Okay, so that's about that basic one. So you get to came across the one concept that's I have said about that W new weight is equal to W volt minus its learning rate divided by DL with respect to W I. So you may get confused about what is that one. Yeah, sure, it's a learning rate. So it's a very important, and because of that all those process going to happen in that neural networks. So it's a very important parameter, and it's called as learning rates. And to calculate the learning rates automatically, there are various optimizers. Okay, so first one is we are going to use that adagrad, and long form is adaptive gradient descent. Okay, so we're going to learn about that adagrad. So in that adagrad what happens here, actually we are going to calculate the learning rate. So here is the learning rate formula also is new learning rate is equal to older learning rate minus, okay, here is also learning rate before that or here is also I can write older learning rate and square root of here is a one parameter comes alpha t plus epsilon. So how learning rate also going to calculated based on each iteration and each epoch, it's here. So here epsilon is a very small positive value, and why we provide here epsilon, because suppose if unnecessary that alpha t value becomes 0, and if you not provide here epsilon, then it's will going to create that matrix, because anything divided by 0 it will going to give you infinite value or going to give error. So to avoid that one, we provide very small epsilon value. Okay, only that purpose. And here is alpha t. So for that alpha t is calculated based on a formula, then it's called as summation I is equal to 1 to time t, where t is the number of iteration at time t with, and we are going to calculate loss with respect to wi bracket square. So that's the alpha t value, and through that alpha t value here all those learning rates is going to changes. So when we place that alpha t value here, you will going to get to know that it's a square type value. Okay, so any number divided by square number, square number, so it will going to give you a very high value at denominator, because it's in the square term. Okay, and that's why if that your denominator becomes high, then automatically your numerator going to become a very low. So indirectly here issue will going to happen, that's here will going to also happen a vanishing learning rate issue, or there will be very small changes in that learning rate. So at one time your learning rate will going to not going to update or change. So that's issue actually happens in that adagrad, otherwise it will be a good. So we move towards the next optimizer, and it's called as a RMS crop. RMS prop, and the long form is root mean square propagation. So it's to improve the adagrad or adaptive gradient descent. So it's used to improve the adaptive gradient descent. So similarly here is a learning rate new is equal to old learning rate minus old learning rate divided by square root of, here we are going to use that weight, exponential weight. Here we call this as exponential weight for plus epsilon. Epsilon is a non-negative number or small positive number, okay, to avoid that issue. And here actually how that exponential weight works, okay, so that's formula is equal to, we are going to give a one term to solve that very small changes that's giving by that diagram. To solve that issue we are going to do that here some terms. So here is beta is a one parameter and its value lies between 0 to 1, and through that value we are going to remove that issue of that square term, okay. So because of that square term, its root square value is going to become very high, and if that value is going to become high, then old learning rate is will not going to change as much as possible, and it will going to not going to make a changes. So to come that issue, we have used that beta value, and here w weight new is equal to w weight old of t minus 1 time, okay, means previous one weight. And here is, we are going to use that formula dl upon dw I square. So let's see now what happens, or I will write here dw old one, okay. So because of that beta value, suppose if I keep that beta value as a 0.95, then what happens, it will going to become a large number, 0.95 into that recently updated weights. Means if you are going to calculate new weight, then it is a recently old weight, plus here now what happens, say 1 minus 0.95, so your value is going to become only 0.05, and 0.05 into, though it's a square term, it's a large term, but it's a 0.05 very small number, so here will not going to get a very high value, so it will be a very small number, anything like that one. So indirectly you will going to get in the denominator a very small number, not that much great number, not very but small number. And because of that small number, if your numerator is divided by a small number, then its value increases, means its value decreases but not as much lower as compared to the greater number, and so your new learning rate will going to changes as per the requirement. Means it will not going to make a very slow changes, it will going to change with a big number. So that's the main advantages of RMS prop, that it will not going to make a vanishing gradient also issue in that learning rate also. So I hope you will understand very well. Now another one is the ADA delta. So ADA delta is similar like to the adagram, okay, please do some research on that. And now very important optimizer, and that's the ADAM, and its long form is adaptive moment algorithm optimizer, okay. So ADAM is nothing but ADAM is equal to RMS prop plus Sgd stochastic gradient descent with momentum rate. So you will you learn about that what is RMS. Now we will going to learn what is Sgd. So before Sgd we are going to learn all those terms such as gradient descent, then another one is mini batch gradient descent, then stochastic gradient descent, then mini batch stochastic gradient descent with momentum. We will going to see the difference in the gradient descent. Suppose if we have 10k or 10,000 points, then it will going to make a epoch on each points for the 10k times. So it will going to do a calculation of 10,000 iteration at one time, then it will going to calculate loss of them, and after that through the backward propagation it will going to update the weight and loss. So it's a very lengthy and time complexity process. For that we are going to convert that 10k data divided by 100. So we are going to make 100 batches. So for each 100 batches, one epoch will going to happen, means one forward propagation and one backward propagation, and through that weight and biases will be updated. So it's faster and efficient as compared to the gradient descent. Okay, but because of that one we have provided a strip size, so it will going to create a zigzag path. Here is a smooth path, but here is a very exponential times, because for each and every point, we are going to make a 10,000 forward propagation and 10,000 backward propagation. For here we are going to make each point only 100 propagation, forward propagation, and 100 backward propagation. So it's faster, but it will going to create a zigzag path because we have provided step size. And in the stochastic gradient descent, what happens? In the stochastic gradient descent, what happens? So here actually what happens, it will going to calculate a loss for each point. Suppose there are 10,000 points, it will going to calculate forward propagation for that point, and again backward propagation for that point, then backward propagation for that point. So it's a stochastic gradient descent. And here in gradient descent, what happens, at a time it will going to calculate the forward propagation for 10,000 points and backward propagation for 10,000 points, but here for single points forward and backward propagation is done. So it's also, though here it's a graph is smooth, but still it's going to give you a requires very large amount of. So here is concept mini batch stochastic gradient descent. So here we provide the batches, and according to the batches it will going to make all those. And here we are also going to provide the momentum to reduce the fluctuation. Okay, so you will going to you get to know what is that mini batch stochastic gradient descent with momentum, and the formula for momentum is equal to there is some formula, please look that formula, it's difficult and I have need to also remind. And so because of that momentum only, here will be a that what we can fluctuation will be reduced and curve will become very smooth. That is the advantage. And so diagram is nothing but RMS prop plus that stochastic gradient descent with the momentum rate, mini batch stochastic gradient descent with the momentum, and it's a very important optimizer, and everyone uses that in the deep learning. Okay, so I think we have covered all those deep learning with the gradient descent, then optimizer, then how we do weight addition and initialization like that. Okay, only one remaining is how we calculate accuracy, so for each method there is a different condition for that one. Okay, if you is going to use sigmoid, then for to predict that does your actual value is near to the predicted value, here is a term binary cross entropy. If it's a binary class, if we are going to use that categorical, then here is simple term categorical cross entropy for multi-classification type. And if you are going to use that Rayleigh or other those functions, then there is another one specific terms, actually I don't know, but I will going to update in that the comment in the next one. So please remember that one. otherwise we have covered all those deep learning parts. Okay, so how we will going to do a project? Initially you need to get the CSV file. Okay, and through that CSV file you are going to create that DF, and I hope you have removed all those outliers, the null, empty values, you have done feature selection and everything. Okay, so I am considering it's a very clean file, and you have just need to calculate x and y, where x is the all those data set df by, and y is the dropped column df dot drop, except x will going to take all those data set for x, and y will going to calculate that dropped column. Okay, so here is our xy data. Now which library you have need to import for that your deep learning? Please remember you have need to install that TensorFlow. You have need to write some libraries such as, I will write here. That's a very important, because interviewer is going to ask you definitely on that one. So you have write that import. Actually in that one interview they have suggested, or they asked me to write that code, import TensorFlow as df. Okay, keras will automatically import it from that TensorFlow. Then import pandas as pd, it's required. Then from keras dot tuner import, here you will going to import some tuned parameters, please remember those names. Then from keras dot tuner dot metric import, you have need to give the those name, that accuracy, then entropy, that binary or categorical entropy name. Okay, like that one. So what is your first step? After that we are going to run that model. So I will going to write here model is equal to, you need to write that tf dot keras dot sequential. Why we are going to use sequential? Because here we are going to add those layers. So it is the first step. So here we have initialized the model. Now we are going to create here input layer. Okay, so now after that we are going to create input layer. So you have just need to write model dot add dot layers dot input. Okay, and in that input you have just need to write here number of columns. Suppose if your features are 24, then you have given to write here some bracket, and like so automatically your input layer will be added here, and that is the very important step. And in that input layer we are not going to provide any activation functions or that checking functions, loss functions, because input layer is not connected to the other, means there are no any addition or initialization of weight and biases, so there will be no issue. Okay, after that input layer we are going to do a hidden layer. We are going to add here hidden layers. Okay, so hidden layers, remember to provide maximum 3 layers, minimum 1 or 2 layers. Okay, there is no any thumb rule. For that hidden layer you need to write command that model dot add dot layers dot, here is one word for hidden, it's hidden. Okay, and after that in that hidden layer you are going to write, initially you are going to write number of neurons in that layers. So initially you should write how many neurons should be in that any layer. Suppose there are 1 2 3 numbers of hidden layers, so first layer you should provide the neurons, and second layer. So in the second layers the number of neurons should be half of that number of features, or half of number of neurons of the input layer. So here we will tell, and in that first and third number of neurons there will be a half of that neurons, so 6 number of neurons. Okay, so I hope you have got the idea. So in that hidden layer I have added those 6 neurons. After that activation function you need to write there like that. Okay, activation function in that bracket is equal to, I will write a sigmoid. Okay, it's a classification function, so I will write sigmoid. And also you need to write here weight initializers, also we can call it as a kernel initializer. Kernel initializers is equal to binary cross entropy. Okay, so it's we have added one layer. So for to add the second layer, you need to write same step. Just you need to write here, instead of 6, here you need to write the 12. You need to write the same step. And for that third layer you need to write the same step. Just be instead of 6, 12, you need to write 6, and you need to write same. Okay, so we have created all those hidden layers. Now last is output layer. So last one is the output layer. Okay, so here is syntax: model dot add dot layers dot output. And here once again, for the output layer there should be only one neurons, because our binary type problem. If you are other types, then neurons depends upon the number of outputs. Here will be activation function. If you are now remember here in the hidden layers, the activation function can be sigmoid, Rayleigh, Rayleigh. But if your problem is binary classification, then you should only use sigmoid function. Okay, only sigmoid function and not other. And for multi classification you should use softmax, and if it's a regression type, then you use a linear unit. Okay, that's sigmoid function. Then kernel initializer to check the weight or like that, binary cross entropy. Okay, now we have created input layer, hidden layer, and also we have created output layer. Now after that you need to compile that model. So you have need to write model dot compile, and in that compile you have need to write here optimizer. Everyone or mostly Adam optimizer uses. And if interviewer will ask what are the other optimizers other than Adams, then those are RMS, crop, adagrad or adadelta. Okay, then after that optimizer, here you also need to write accuracy terms. Okay, so we have compiled that model here, and also here you need to write okay, that one. After that you have need to train that model. Okay, here you also need to write to epoch size. Epoch is equal to 100. Okay, so epoch size will be, that model will going to do each forward and backward propagation on each layer to calculate weight and updates. After that model compilation, we are going to do a model dot train, and here your value will be x train comma y train. Okay, and any other parameters. So indirectly you will going to train. After that you will print model dot summary. You will going to get here which initializer or which kernel is great, and after that you are going to calculate that model dot accuracy, and you will going to get the how is model you will going to give accuracy and like that. Okay, after doing that, the definitely steps we have need to do a next one step, and it's called as a hyperparameter. Hyperparameter. Please remember, for that deep learning also there is a hyperparameter. Okay, so before creating hyperparameter you also need to create that my callback function. My callback function is equal to self comma callbacks comma callback, like that one. So how you use the create that callback function? Get dot log of that accuracy. So we calculate the accuracy value and we give here condition. If that accuracy value is greater than 90%, then please stop, means we write here print stop epoch. Our accuracy is achieved, because if you give the 100 epochs and suppose your accuracy is get at the 30 points, 32 epoch, then still your system will be going to run all those epochs without any, though there will be no any change in the learning rate or anything. So to stop that, and to get rid out of that time, we are going to do that my callback function. Okay, after creating my callback function, we create the hyperparameter function, hyperparameter. Okay, and in that hyperparameter we are going to use two types, hype.int, and in that hype.int we are going to use going to function hype.int. Here we are going to set the range minimum comma maximum, and here we are going to provide the step size. So minimum is the 6, maximum is the 36, and here is the step size is the 6. So how it will going to create number of hidden layers. So here we are going to step size 6, so 1 6 and 6, like that, means 6 12 6, it's like that, it's given we have step size. So it will going to create 3 hidden layers with each layer containing 6 number of neurons, another one is 6 neurons, and third one is 6 neurons. Okay, so it's very important. And we are also going to use hype.choice function, and in that hype.choice function we are going to provide that list type value. Suppose if you want to use that two activation functions, such as one is that sigmoid and another one is Rayleigh. So hyperparameter will be going to select which better, and it will be going to do a performance on sigmoid and Rayleigh, and it will going to give a best one, which will going to give a best value. Also through that you are going to also provide that optimizers, Adam optimizers, such as will to choose the Adam or RMS crop based on that condition. Okay, also through that you are going to provide that entropy binary cross or only cross entropy. Also you are going to provide that weight initializers, such as glorot uniform or glorot norm, or like that one. Okay, it's very simple, because but I want to cover all those in just 1 hour, this time is extreme. So through that hyperparameter we all process all those steps. Once again through that hyperparameter we create the input layer, then we create the hidden layer. In that hidden layer we all those process all those value in the list, and we create the output layer. After that we compile that model. In that compile we call the callback function, and in that compiles also we provide that optimizers, such as Rayleigh. No optimizers, here we provide that Adam or RMS crop. Here for the accuracy we also provide that binary cross entropy or that other one. Okay, and after that we also train once again model, and once again lastly we calculate the accuracy, and if we got the satisfactory accuracy, then we consider that our deep learning project has been successfully developed, deployed. After that joblib or pickle file, through that joblib or pickle file we actually dump that model on that web server through Flask or AWS, and indirectly our project has been successfully deployed. And that's about whole the process of project. So I have covered all those in just 1 hour 15 minutes, all those deep learning concept with very layman and simple terms. And also I have taught you how to that make a project end to end. Please do practice. If you have any doubt or issue, please ask in the comment, and please give me feedback about my lecture and video. And please enjoy learning, it's very interesting, and I have covered all those questions mostly interview can be asked. So thank you very much guys. I'm going to stop that lecture now.